So let's take a look at a shortcut for how I can use integration by parts, but in a slightly faster way. We'll call this shortcut tabular integration by parts. Now, this is a theorem, which means it's a big result within mathematics, and most theorems have a very kind of common rhythm to them, as we'll see throughout the rest of this semester. But they often have a set of conditions, like we saw in Chapter 2, and then a conclusion. And it's very important to understand the conditions, because if you don't check the conditions, you might inappropriately apply this idea. So let's see what we have here. This theorem starts by stating, suppose p of x is a function, but let's suppose that it is a polynomial function. That's why I wrote it with a p for polynomial. And let's suppose that it's of degree n. Remember, that means that the highest exponent occurring in it is n. Okay, we'll say that that's, again, some natural number. It's got to be some whole number value up there. And we'll also suppose that we're going to have a whole bunch of other functions here. So I'm going to write out a big list of functions. These are going to be our capital F functions. I'm actually going to number them off. I'm going to have f number 0, f number 1, f number 2, and in fact this list is going to go on and on and on for a while. I'm going to stop once I get all the way up to f number n plus 1 of x. So notice here that the number of f function, I go all the way up to whatever the degree of that polynomial was, plus one more. So if I had a polynomial of degree 2, like a quadratic, I would go all the way up to f number 3. If this was degree 10, I'd go all the way up to f number 11. Now, if p is a polynomial function, what the heck are these f functions? Well, let's suppose that these are functions such that f of I plus 1, so that is, if I picked a number to plug in place of I, and then I added 1 to that, so it's kind of like a function over on the right somewhere, like a higher up function. This is an This is an antiderivative of f little I of x for each I that goes from 0 up to n. Okay, now that's like super mathy sounding, but to break it down very simply, what we have here is kind of a hierarchy of functions. The functions over on the right, these functions are all antiderivatives of the functions that come right before them. So f0, when I take its antiderivative, I get f1. Take that antiderivative, I get f2. Take that antiderivative, I get f3, and so on. Or you could imagine going in the opposite order. Take the derivative of fn plus 1, you get fn. Take the derivative of f2, you're down to f1. Take the derivative of f1, you're down to f0. So these functions are related by derivatives or antiderivatives, depending on which order you're looking at them in. So if I have all of this set up, then I can say the following. I'll say that then we have that if I was interested in doing the derivative, or sorry, the antiderivative of p of x times f0 of x dx, there's a way to do this. Now you might recognize that this would be pretty easy to do with integration by parts, at least at the onset, because I have something easy to take a derivative of in p of x. It is a polynomial. And it's actually really easy to take an antiderivative of f0 because I know it's f number 1. So I could start doing integration by parts, but I'm actually going to have repeated integration by parts happening here, and I'll actually be able to tell you exactly what the grand total result is going to look like. The grand total result is actually going to be a bunch of things added or subtracted together. You can see that even in our past several examples. I'll start this by saying I'm going to start at thing number 0 and actually go up to thing number n. Now, not all these things are necessarily going to be positive. Some of them might be negative, some of them might be positive. And so I'm going to start by actually putting here in the front a -1 raised to a power of I. What this is going to tell me is that the things that are going to be in the answer to this are either going to be positive or negative, but they're going to alternate. At least this sign is going to help them in the alternating process. I can then actually have over here p I of x. Remember that when I put that little I in a parenthesis up there, you might recall from Calc 1 that that means I'm going to be taking an ith derivative of p. So if that says I is 0, that says take 0 derivatives of the polynomial and just write it down. If that I is a 1, it says take 1 derivative. The last part that I have here is going to be this fi plus 1 of x plus c. Okay. Now, keep in mind that that plus c is outside of this summation. So after I write all this, then I put my plus c. So this is, again, a very strange formula, but we're going to be able to kind of summarize what's going to be happening here very, very easily. What you'll notice is that there, again, are three things that are going to compose each one of these different terms inside of this, inside of our answers. I have this -1 piece to a power, so I'm either going to get a negative or a positive on each item. I'm going to have my polynomial or one of its derivatives, and then I'm going to have an f or one of f0 or one of its antiderivatives somewhere up the list. To summarize this, let's take a look at an example like this. I want an integral of an x squared times a sine of x dx. To visualize how I can easily use this formula, to make this a really fast shortcut, I'm going to go ahead and I'm going to draw out a quick table. I'm going to give this table 3 columns to stand for these 3 items that I have up in here. So my first column is actually going to stand for my p of x's. My second column is going to stand for my f's, which start at f0. And my last column is going to stand for like a plus or a minus, coming from this -1 to a power. Now, I'm going to start here by immediately writing out what my polynomial was in this case. Notice I have a polynomial, so I know this shortcut's valid. I also see that the sine of x would then be my f0. And does the sine of x have a lot of antiderivatives that I could find? Like, could I find a whole bunch of antiderivatives for the sine of x? Well, yeah, because like I can, antiderivative of sine is negative cosine, and then I could find the antiderivative of that, and I could keep going. So what I'm going to do is get ready to fill all this stuff in. Now I'm going to go ahead and I'm going to start taking derivatives. I can see here that I'm going to need lots of derivatives for my polynomial. And I'm going to keep taking derivatives actually until I hit 0, which here doesn't take too long. Once I have that, I'm going to start doing antiderivatives in the middle column. We already said antiderivative of sine is negative cosine. Antiderivative of that is negative sine. And the antiderivative of negative sine is cosine. Now, over here at the edge, I'm going to go ahead and do something that's going to look kind of strange at first. I'm going to actually put like a skip, like a blank space here. And then I'm going to put a positive, a negative, and a positive. These are going to be like alternating symbols. No matter how long this list was, it would alternate. And I'd like you to see how what I'm about to write down corresponds precisely to the items that I have up here. I'm going to find the 0th item that comes out of this summation. And I would say, first I'm going to have 0 derivatives. That's this guy right here, 0 derivatives of p. And I'm going to link that together with the first antiderivative of my starting f. Then I'm going to multiply that to -1 to the 0th power, which would be a positive 1. I can then see that if I go to the next term, this is when I would be a 1. I would do a first derivative, another antiderivative, and I to the first power would be negative. Notice I can kind of create this pattern going all the way down, and I know that these are the 3 components that need to be multiplied together to create a term here. So, by tabular integration, what I end up with is that my integral x squared times the sine of x, take a look at how beautiful this is. It's going to be these 3 items multiplied together. Notice if it's helpful, you can imagine these as plus or minus 1s at the back. So I'm going to have a negative x squared cosine x. I'm going to have a Let's see, what is that going to be? It's a negative sign times a negative 1. That's positive sign, so it's going to be a positive 2x sine x, and then plus a 2 cosine x, and then plus a c. Boom! An instant answer created. Now, you may not have caught this right at the beginning, but didn't we do this question already? Yeah, we actually did this question just a little while back in the last video. We actually took a look at this as example number 3. And I'll see if I was to go back and look. This is the same result as in example 3. Let's actually take a look, right? If I go back to example 3, look, here it was. Integral of x sine of x. We had to do integration by parts 2 times here. But this tabular integration by parts essentially gave me this powerful shortcut to just immediately jump to the answer. Negative x squared cosine x, 2x sine x, 2 cosine x. Don't forget the constant at the back. Notice that's exactly what we got here. That's a really powerful result. In fact, I would ask you to go ahead and see if you can try to do this exact same thing on your own here on example number 4. I won't create a video for this one, but you of course can go ahead and check the solutions as you try this problem with the notes that are posted up in Blackboard.